Hello everyone. My name is Jenny Gardner and I'm a math coach with the academic support team here at SNHU. Welcome to this guide on the linear regression equation, which actually has quite a few names. So if you've heard it called something else along the way, you'll understand that it may have multiple names. Today, we will be discussing first the definition of the equation and what it does, then how to find the linear regression equation using a couple points that could be provided to you. And finally, using data to create the linear regression equation and then interpret. So what is a linear regression equation? Well, it's notated like this, but it has a couple other ways it's notated with symbols. So sometimes it says EY instead of that Y hat with the little hat here. That's called Y hat, but if it says EY, that means expected Y, and it can be notated either way. It might also, instead of slope, say B1 or beta 1. X will be X, should remain X, that's the variable. It's not a specific number necessarily, it means all possible X's within the data. And then intercept is written as beta 0 or B0 sometimes. Another way you could have seen this is written as Y equals mx plus b. Any particular way you see it written, it means this middle one. It means that we can predict y based on the slope times x plus the intercept. This equation lets us predict y. However, you can't always predict y. It actually has to have a relationship between x and y before you can do it. It must be correlated, must be linear for us to use this equation. And there is a video that will be in the video description that explains how to figure out if something is correlated visually or with the correlation coefficient. So that should be the first step before moving on to creating the linear regression equation. But we're going to make a line function based on 2 points. So let's say, for the sake of this example, that x and y are correlated. And now we have 2 points that have been given. And a point is written x, comma, y. So we have x1 and y1 here. And then we have a second point for x2 and y2 over here. And this is a comma. So we have 2 different points provided, and we're going to use those to make the equation. And the first step is to find the angle of the line, the slope. So on a graph, that would be the angle of the line, the way that it is diagonal. How much change is happening? So for every change in x, as it's going 1, 2, 3, as it's going in this direction, how much is it going up? That's what the slope tells us, the change. So to do that, we take the second y, 850, and we subtract our first y, 250. And that will be over x2 was 3, and x1 is just 1. So the y points get subtracted, and the x points get subtracted. So we see 850 minus 250. Okay, so if you do that on a calculator, you should get 600. And on the bottom, if we do 3 minus 1, you should get 2. So now we have 600 over 2. That means divide. 600 divided by 2, which is going to be 300. So our slope is 300. Slope, 300. Now let's find the y-intercept. To find the y-intercept, we have to use the equation. The y equals the slope times x plus the intercept. In order for us to find the intercept, we have to put in some of these values and solve. So y equals, the slope is 300. We know that, that's here. I'm actually going to leave a blank here for x, and then I'm going to write plus intercept. So I actually know some other stuff already. I know a point for x and a point for y. I actually know two of them, but I only need to use one of them. And so we are going to use, let's use the first one. So when x is 1, y is 250. Okay, when x is 1, y is 250. So on a calculator, just a regular old calculator, and I want you to pause this and try this out. We can solve this. So from here we know 250 equals 300 times 1. That should just be 300 plus the intercept. Okay, well, now we have 250 equals 300 plus the intercept. So if I want to move the 300, I will subtract it. Minus 300, I have to do the opposite. It's being added, I'm going to subtract. It's positive, so I'm going to subtract. 250 minus 300 becomes a negative 50 is our intercept. Because 300 minus 300 is 0, but 250 minus 300 is a negative 50. And so our intercept we just found is a negative 50. That's the point where it hits our axis. So way down here at negative 50 on this graph, it would hit our y-axis at negative 50. And so now we can put it all together. We have both values. We have our intercept and our slope. So y equals the slope times x plus the intercept. Well, we can estimate y by having 300 times x plus a negative 50, or minus 50. Plus negative is the same thing as subtracting. So this is our linear equation based on those 2 points, right? So we were able to figure it out just based on 2 points. And now we're going to look at how to do it with data. But if that was confusing, I want you to rewatch it. Sometimes you might just have the points given to you and you can go from there, but other times you actually need data. And we're going to talk about how to interpret when we get to the data specifically. But as we see, along the way, we talked about the fact that the slope shows the change as x is increasing by 1, y will increase the amount of the slope. X increases by 1, y increases the amount of the slope, or decreases if it's negative. Then the intercept is the starting point. When x is 0, y is going to be the intercept, negative 50 in this case. So we'll get further into that after we look at our data solution here. So let's say that we have collected data about an adoption program for dogs, where we want to see the total donations and how they change based on the extra services provided. So the initial adoption happens, and then they can add stuff like a collar, tags, shots, and grooming. And as those things are included in the adoption, how much does the donation change? Do they donate more? Do they donate less? Well, let's see what happens. So we are going to interpret the slope and see what happens there. We're going to interpret the y-intercept, and then we're going to interpret the entire equation. But first, before we can do that, we have to get the values. So we are going to go over here to my lovely Excel sheet, and we see that these are the dogs that have been adopted. Fun fact, 2 of these are my actual dogs, and quite a few others are coaches here at SNHU, academic coaches. So see if you can spot some of the names, and I'll tell you who my dogs are at the end. Take a guess, see if you're right. All right, so we have these dogs adopted, and these were the extra services added, but I forgot to include the donation amounts. So Let's say that I had someone who had 0 extra services added. We didn't provide them any services for this donation place, and they donated $50. And so now we're going to see what everybody else donated. This person who adopted K9 donated 300, this one did 200, this one did 150, and so on. So we've got a bunch of different dogs here. I'm on Gregory the Third now. And different people adopted and donated different amounts, and we have to see if that made a difference. When they were provided these services, what did they do? Almost finished now. Okay, so we had these donation amounts. So we have to decide which one is our X and which one is our Y. So X is going to be the one that is used to predict, and Y is the one we're trying to predict. So we're trying to predict how much someone donates based on the extra services that we provided them in this dog adoption program. So that's what we're trying to do. So extra services is the explanation, so it's X, and then donation amounts is the prediction, and that's Y. That's what we need to predict. Okay, so here we go. Let's do it. Up here under data and data analysis, and there is a previous video on descriptive statistics where I explain how to get that if you don't have it. I explain how to search for it, where to find this add-on, but this is the one we're going to use. And when we go to data analysis, there's a whole bunch of things here, like central tendency can be found in descriptive statistics. You can make a histogram, lots of stuff. But we're going to go to regression because this is the linear regression equation, right? Regression is going to provide us with a lot of details that are useful. One, it's going to tell us if they're correlated, which is useful for sure. And then it'll also tell us the slope and the intercept. So input Y range, well, this was our Y. Click and drag. See how I just clicked and dragged that and now it's typed in? Input X range. So I'm clicking here, click and drag, let go. Good. And that's it. All this other stuff is extra. You can do it if you want to see it, but we're not going to do it for this particular one. We're just concerned with the linear regression equation. So I'm going to hit OK. All right, so it gave us lots of information. I want to tell you the things you use depend on how far you are in statistics. I'm just making a column so I could write. When you're working with basic level statistics and you're looking at just focusing on the regression equation and correlation, then the only things you really use are the top two and the bottom two. This is R. There's a whole video on the correlation coefficient R as well. Look in the video description to find any of our other videos. This is R, and this is R squared. Both of those are values that are important, but not to our linear regression equation. But what it is important is knowing if it's correlated. And what we see is that this has a moderate correlation, 66% correlated. So it's not super strong, not a super strong correlation, but it's not super weak either. It's about 66% correlated. So that means that X and Y, we can predict, but we're not going to get an exact value. It will be a moderate correlation, which means we'll have moderate results. So about 66% of the time it might be predicting, and we'll see what happens. This one here says intercept. This is the Y-intercept, and this is the slope. So the top two tell us how much they're correlated, and the bottom two tell us our information for the regression equation. R squared has a slightly different definition, and it would be really good for you to look it up and understand it so you can interpret what R squared is telling you. Because R tells you how much something is correlated, and R squared tells you how much variation is explained. So both of them are percentages, both of them tell you something different. Great to go investigate that further. But right now, we care about these two. The intercept, the slope. Intercept, slope, intercept, slope. So right here, intercept, right here, slope. We have our numbers. I am going to, let's see if it lets me copy to the other page. And it does. Awesome. So we have the intercept and we have the slope, and now we need to make our equation. Okay, and so we'll go do that. But before we do, I told you I'd tell you which ones were my dogs, and K9 is one of my dogs after the Doctor Who show, robot K9 dog, and Athena is the other dog that I have. So I have two, K9 and Athena. There's lots of names in here that are representing our team, and I'll let you figure that out. But here is our intercept and our slope. So let's go and try and go back and create it now. There it is. I did it too many times, but okay, so we have our information. I just copied that over. Okay, so we have our intercept and we have our slope. And so the first question is interpret the slope. All right. So for every change or every extra service added, how much will the donation change? Well, it'll change by the amount of the slope. That's what the slope tells us. So for every for every X, that's the extra service added, the extra service X, how much will the donation Y change? Well, it's going to change by $80.84. And it's a positive, so it's going to increase and go up by $80.84 every time. That's the slope. Interpreting the Y-intercept. When there are 0 X's added, no extra services, 0 extra services, how much is the donation? Well, that's the intercept. The intercept is predicted to be $66.07 if I round. That's how much it's predicted to be when there's 0 extra services. So when X is 0, Y is predicted to be 66.07 because that's what the Y-intercept says. And for the entire equation, we can predict Y, the donation, by taking the slope, 80.84, multiplying by a value for extra services, plus the intercept. So this is the equation. So let's try it with 5. If there's 5 extra services, what will the donation be? 5 is just an arbitrary number. We could do 2, we could do 3, and you should try it on your own and see what happens. But we're going to do 5. And when we say 80.84, we're going to predict the donation by taking 80.84 and multiplying it by what? Think about that for a second. What do you think? Pause and take a second to think because I'm going to tell you. We're going to multiply it by our X value, which is our lovely 5, because that's what the problem says. It says 5 extra services. So this will be multiplied by 5, replacing X with 5, and then we're going to add that 66.07 still. We have to remember to include that because that's our intercept. So that's like the baseline value. 0 services, they're going to donate approximately $66. But every service added is going to be an extra 80.84. So if we do this formula, 80.84 times our 5 services, that's going to be 404.2. And then we have to remember to add in the 66.07. And after we add 66.07, our prediction for what Y is going to be with 5 services is $470.27. So every time they donate, every time a service is added, they donate about $80.84, and that lets us predict that if they get 5 extra services, then they're going to donate $470.27. So this is how we use that equation. We can predict what will happen. okay? That is why it is super beneficial to learn this. We're trying to predict the average. And now that's not saying that every person, every single person who gets 5 services is not going to donate $470.27. In fact, let's go look at our graph, our data here. This person who adopted K9 donated $300. So we just said we predicted that they were going to donate based on the equation, this 470.27. That's what was predicted. But the actual was 300. So the difference, also called a residual, the difference is going to say the actual minus the predicted. Actual minus predicted. Actual minus predicted. Because this is just an average donation. This is just an average donation. It's not an exact value. And so we see that the actual person was below the average by $170. So minus 170. Whereas this person who donated 900 when they got 5 services, if we do actual minus predicted, equals 900 minus the predicted, we see they are above average. So this person, above average, this person, below the average. And that's how it truly is. When we have a prediction, there's going to be some above and some below, and we can see what the difference is by calculating the residual. And now we know how to work with the linear regression equation. So, thank you so much for watching our academic support video on linear regression equation. Congratulations on making it through. And please see the video description for further resources. Have a marvelous day.